Hey everyone, Garrett here. We're going to be talking about some really exciting news today, so stick around for that. I wanted to give a shout out to all my subscribers. Thank you so much. If you have any comments about how I could improve or what topics I should be covering, go ahead, post those in the comments, and then we'll get started here shortly. But first, I have to make some coffee. Alright, well, what we're talking about today is going to be a radio telescope on the moon. So, NASA reveals wild project for turning a moon crater into a radio telescope. NASA just gave out a new round of grants for its favorite up-and-coming innovative space projects, one of which is the plan to fit 1 kilometer radio telescope inside a crater on the far side of the moon. The Lunar Crater Radio Telescope, LCRT, would be able to measure wavelengths and frequencies that can't be detected from Earth, working unobstructed by the ionosphere. Working unobstructed by the ionosphere or the various other bits of radio noise surrounding our planet. Okay, we'll get to that later. So, this Lunar Crater Radio Telescope is going to be a huge satellite dish inside a moon crater. So the moon crater itself is going to be 3 to 5 kilometers in diameter. If you're not familiar with kilometers, 5 kilometers is about 3 miles long. So we're talking about a moon crater 3 miles in diameter, and that's pretty massive. The deployable wire mesh is going to be 1 kilometer in diameter. So the effective area of the satellite dish is going to be 1 kilometer in diameter. So, and then it's going to be on the far side of the moon. So, the moon is tidally locked with Earth, which means it doesn't rotate in its orbit. So, the same side is always facing Earth. That's why some people call it the dark side of the moon, which doesn't really make sense because if the moon's in between the sun and the Earth, that side's not dark anymore. It's just, we don't see it. So it's the far side of the moon, and it's always going to be facing away from Earth. So one of the reasons we want to build a radio telescope on the moon is to reduce overall interference. The atmosphere of Earth can actually interfere with the electromagnetic radiation coming in. And given the radio waves, the atmosphere doesn't play as big of a role in interference with them because the radio waves actually don't interfere with the atmosphere on a huge order. However, the satellites orbiting Earth play a huge role in interference with radio waves. They emit radio waves, and also they can block radio waves, and the radio waves that they emit can constructively and destructively interfere with the radio waves that we actually want to observe far off in the universe. Later. So, LCRT could enable tremendous scientific discoveries in the field of cosmology by observing the early universe in the 10 to 50 meter wavelength band. So we're talking about wavelengths from 30 to 150 feet in length. As per the plans, the moon rovers would pull out a wire mesh some 1 kilometer across inside a lunar crater. Then could be that, I think that's a typo, that could be up to 5 kilometers in diameter. Everything could be automated without any human operators, which in turn could mean a lighter and less expensive payload for the project to literally get off the ground. It is still at the very early stages of planning, and it's not clear yet exactly which crater would be used for the job, but it is an intriguing concept, and we'll be keeping an eye on this in the years ahead. The biggest radio telescope here on Earth is 500 meters in diameter. It's called FAST, or FAST. It's located in China. And then we also have another very popular radio telescope that's in high demand. It's called Arecibo, and it's located in Puerto Rico with a 300-meter diameter. And I'll show you those two in a bit. So the automation plan for setting up this telescope includes a telescope lander goes to the crater center, and then the duaxle lander to the surface. So the duaxles are going to go into the crater, grab onto the net, and then pull the net across the crater and then back out. And then they're going to anchor in on top of the crater. So China and the Netherlands have already set up a radio telescope on the far side of the moon, albeit a much smaller one. This telescope uses satellites to relay data back to Earth like the LCRT will have to do if we pull it off, right? Because they're not going to be able to communicate through the moon, so they're going to have... So I'll show you later, but basically the radio telescope that China and the Netherlands set up on the moon is called NCLE, and they have a satellite orbiting the vertical plane of the moon, and that's going to send radio waves back to Earth. So by building the largest filled aperture radio telescope in the solar system on the far side of the moon is bound to create a lot of public excitement. Alright, so that's it for that article. I want to show you guys what Arecibo looks like. So this is Arecibo. It's got a 300-meter diameter. So that's about 900, almost 1,000 feet in diameter. And then this aperture here is the data center, and it's suspended in the air, all radio telescopes. So basically what's happening is the satellite dish is focusing the light waves into this aperture here. And you can actually rotate and move this aperture along the top of the dish. So that's in Puerto Rico. Next up is FAST, F-A-S-T, and this is in China. So this satellite dish is 500 meters in diameter. So that's really big. 500 meters is about 1,500 feet, 1,600 feet. So it's really large. And the one on the moon is going to be double this size inside a crater that's 10 times that size. So, yeah. So here's another article from Science Alert. There is now a radio telescope in operation on the far side of the moon. This was made a few months back in December 2019. And basically what they did was they have a whole unit. So the LCRT is going to have to be assembled on the moon, while as the NCLE was a single unit that got sent to the far side of the moon, and it basically just had to unfold its arms. And they kind of had issues unfolding the arms. It kind of stopped halfway, and so they decided to just stop there and start collecting data instead of risking breaking something, because that would really suck. And basically what you have here is the orbit of the satellite that's in communication with Earth. So in this orbit, it's in the vertical plane of the moon, and in this orbit the satellite is in constant communication with both the radio satellite and Earth. So it's actually a really clever idea. While the NCLE is capable of mounting multiple forms of scientific research, its main purpose is to conduct groundbreaking experiments in radio astronomy. Particularly, the NCLE will gather data in the 21 centimeter emission range, right? So remember what we were talking about, 21 centimeters, that's 0.21 meters. That's like a foot, all right? That's not that much. The LCRT, we're talking about 150 foot wavelengths, okay? So much larger, much more capable, and it's just kind of weird that they sent It's kind of weird that they sent a radio telescope to the far side of the moon that has a lot of the same capabilities as telescopes here on Earth. So here's just a Big Bang model. And then, so this is the satellite that's orbiting and it's sending stuff to Earth. So at their current shorter deployment, the instrument is sensitive to signals from roughly 13 billion years ago. Once the antennas are unfolded to their length, they will be able to capture signals from just after the Big Bang. This will allow astronomers to see the very first stars being born and star clusters coming together to form the very first galaxies. So I know what you guys are thinking, right? You're saying, well, I've never seen a radio telescope in person, so I have no idea how big it is. And I would say, yeah, me neither. But if you've ever played Battlefield 4, chances are you actually have firsthand experience of how large these things can be. So one of my very good friends, Cameron, sent me this Battlefield 4 footage just so I could show you guys how big these satellite dishes are. And I think this one is based off of FAST, F-A-S-T, in China, so it's probably about 500 meters in diameter. And just take a look at this because it is really large. So you're going in, and here we'll just freeze frame right here to just kind of get a picture of how large this thing is. So as you can see in the center, remember when I showed you Arecibo, there's that big data collection light gathering point. Well, it looks like in Battlefield 4 that fell onto the dish. And yeah, so we're talking about on the moon, the crater is going to be 10 times as large as this dish right here, okay? And the actual dish is going to be double the size. So the net itself, the effective satellite dish, is going to be double this size, but the crater itself is going to be 10 times the size of this dish. So how do radio telescopes work, and why do we need them? So here I have the electromagnetic radiation spectrum, and this shows basically the wavelength of the certain types of electromagnetic waves. And right here, this tiny little sliver is going to be the visible light, and this long piece right here, these long wavelengths, are going to be the radio waves. As we get higher up into the spectrum, we're going to get lower wavelengths, higher frequencies, and higher energies, because the wavelength actually decreases the higher the energy and the higher the frequency. And then the lower the energy, the lower the frequency, the wavelengths increase. And so that's why we have really, really, really large wavelengths in the radio wave spectrum. And so in order to capture these really large wavelengths, we need to have satellite dishes that are really large as well. So, right, we're talking about 1 kilometer satellite dish to capture 150 meter wavelength. So that's about, it's almost 10 times as large as the wavelength itself. So why is this important? What can we observe with radio waves? We can observe what's called hyperfine hydrogen transition or a spin flip transition with hydrogen. They're the same thing, 2 different names. Really complicated quantum mechanics stuff, not going to get into it, but basically there's a transition in hydrogen that happens that emits radio waves. And when we observe those radio waves of that specific wavelength, then we know that whatever sent it, where it came from, there's a source of hydrogen there. And so that's exactly it. Okay. Hey everyone, thanks for watching. The next video I have is going to be one of the brightest supernovas ever observed in human history. And if you liked this video, go ahead, hit like. And if you have any comments, suggestions, or tips on improvement, please let me know in the comments. And if you don't want to miss the upcoming videos, definitely subscribe so you know when they drop. So, thank you.